Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the online data structure class. What we will be doing today is to start the third online lecture on chapter 5, which is on hashing. Today's topic will mainly focus on quadratic probing, which is one of the collision resolution method. Quadratic probing eliminates linear probing's primary clustering problem. Since in linear probing the collision function is linear, similarly in quadratic probing the collision resolution function is quadratic. And popular choice for the quadratic function f is input I, which equals I squared. Now this approach eliminates the primary clustering problem of linear probing. H of I of input key x equals to hash of input key value x plus variable I to power square, where I equals to 0 in the first sequence. For the second sequence, I equals 1. For the third sequence, I equals to 2, and so on. If the hash function evaluates to hash value and a search cell is full, we try cell h plus 1 to the power square. If that's full as well, then we try h plus 2 to the power square. If it's full as well, then we try h plus 3 to the power square, and so on, following h plus I to the power square. Thus, we have examined cells 1, 4, 9, and so on, away from the original probe. Suppose that an element should appear in bin H. If bin H is occupied, then check the following sequence of bins: H plus 1 square, then H plus 2 square, then H plus 3 square, then H plus 4 square, then H plus 5 square, and so on. For example, M equals 17, where M is your table size of 17 bins. Pictorially, you will observe the indices on the hash table array from 0 to 16. Suppose if bin 3 is occupied, which is a yellow color marked bin, then check the following sequence of bins. First one is 3 plus 1, which equals 4. Your first check will be bin 4, whether it's empty or not. Let's assume that it's not empty. Then your next sequence will be 3 plus 4, which equals 7. If again bin 7 it's already taken, then your sequence to check will be 3 plus 9, which equals 12. If bin 12 is already taken as well, then you check the next sequence, which will be 3 plus 16, which equals 19. Now hash table size is 17, and we need to insert in bin 19. What do? We do wraparound. Once we reach bin 16, we do wraparound to index 0, which marks us to bin or index 17. then index 1, which again marks us to bin or index 18, and finally index 2, which marks us to bin or index 19. Thus we try to insert in bin 2. In case bin 2 is not empty as well, then we apply the next sequence, which would be 3 plus 25, which equals to 28. We will be trying to insert in bin 11, and you can check for yourself. If one of quadratic function h plus I squared sequence falls into a cluster, this does not imply the next one will. What implies here is that pictorially, if we observe the indices from index 2 to 8 of the hash table, that's a cluster where all the bins are taken. Now, taking the same bin 3 example, where we would like to hash in, if your first quadratic sequence happens to fall into this cluster, which will be bin 4, or for the next sequence, which will be bin 7, although both are within cluster range, taking a sequence further will end you in bin 12, which is out of bounds of the cluster. With quadratic probing, which is instead of moving one spot all the time like we did in linear probing, we move I² spots to avoid collision. It solves the problem of primary clustering. Unfortunately, there is a second problem which must be dealt with. Suppose we have table size m equals 8 bins. Then 1 square equals 1, 2 square equals 4, 3 square equals 9, which basically equals 1 if we apply wraparound. Now what it implies here is that when a collision happens in any of the bins, the next index chosen is in a fixed manner. We are adding the following set of random numbers: 1, 4, 9, 16, 25, so on, one by one to find an empty bin where we can insert the element. Instead of having new set of random numbers when we hash to the same bin, if it's full, we are using the same old set of random numbers when a collision occurs. Suppose for table size m equals 8 number of bins, we are hashing to bin 0. If we apply quadratic probing, then our first sequence will be bin h plus 1 to the power square, which equals 0 plus 1 equaling 1. Second sequence will be bin h plus 2 to the power square, which equals 4, since h is 0. And the third sequence will be h plus 3 to the power square, which equals 0 plus 3 to the power square, which equals 9, which equals 1, again if we apply wraparound. You can observe that in this case we are checking bin h plus 1 twice, having checked only one other bin. meaning we have checked bin 1 twice during first sequence and third sequence. The modulo operator, which is applied with respect to the table size m, which is h plus I square, the whole term mod m. There is no guarantee that we will cycle through all the bins of the hash table from 0 to m minus 1 in order to find an empty bin such that we can avoid collision. The solution here is that the table size m should be a prime number. Otherwise, the problem where we are not sure that we will probe all the locations in the table will be much more severe. In this example, we have I square mod table size computed, that is, for I equals to 0, 0 mod 11 equals 0, for I equals to 1, 1 mod 11 equals to 1, for I equals to 2, 4 mod 11 equals to 4, and so on, till I equals to 6, 36 mod 11, which equals to 3. The probe sequence will be h of k plus 0, then h of k plus 1, then h of k plus 4, then h of k plus 9, then h of k plus 5, then you will have h of k plus 3, and then again you're going to have h of k plus 3. If you map the probe sequence into the array, you can observe that we were able to put the first 5 sequences in separate slots, but 6th and 7th sequence cycled to same array index of 3, causing a collision, meaning the sequence is not cycling through all the bins of the hash table such that collision can be avoided. Now, if you increase the table size m equals to 13 and repeat the same process, you can observe that 7th and 8th sequence cycled to same array. Similarly, if you further increase the table size m equals 17 and repeat the same process, you can observe that 9th and 10th sequence cycled to same array index of 13. We were able to put the first 8 sequences in separate bins. Thus, quadratic probing avoids primary clustering. This helps to avoid the clustering right around the collision. Basically, it spreads out the keys more. Unfortunately, we are not guaranteed that we will use all the bins of the hash table, just like you have noticed in the above 3 examples. In reality, if the hash function is reasonable, this is not a significant problem until load factor lambda, which is total number of entries divided by the table size, approaches 1, when many keys are hashing to the same index of the hash table. Let's look at an example where we have a hash table with table size m equals 19. Now, by using quadratic probing, let's insert the following 3-digit random numbers in the following sequence. The random numbers are 86, 198, 466, 709, 973, 981, and so on, and the last random number is 565. We will use the number modulo 19 to be the initial bin, meaning let's use this value as the hash value. Now further to insertions, for random number 86, we will have the hash value computed as 86 plus 0 squared, whole term mod 19, which equals 10. So we insert it into bin 10 of our 19 array size hash table. Similarly, for random number 198, we will have the hash value computed as 198 plus 0 squared, the whole term mod 19, which equals 8. So we will insert it into bin 8 of our hash table. Thus, the first two numbers, 86 and 198, fall into their correct bins. For random number 466, the hash value computed as 10, but bin 10 is already taken by random number 86. It already causes a collision. Thus we further increment the quadratic function I to 1 and compute the hash value as 466 plus 1 squared, the whole term mod 19, which equals 11. Bin 11 is empty, therefore we insert into it. Now if we compute the hash value of random number 709, it will fall into bin 6 without a collision. Similarly, for random number 973, 981, and 374, they will fall into bins 4, 12, and 13 respectively of the hash table. Then another collision is caused when we take the hash function of random number 766, which gives us bin 6 index in the first sequence, which is already taken by random number 709, and bin 7 index of the hash table in the second sequence, where we insert it since it was empty.